At one point in time, this talk, which is now part 2 of N, or part 2.4 or so, because I've given various versions of this, but it started out as part 1 was an overly complicated lock-free queue. Got simpler along the way, which was good. Started getting more complicated. I don't know, we're somewhere in the middle. Before I even start anything, I always let people know that this is the stuff I really work on. You take a bunch of projectors and you turn them into one projector. Do it on flight simulators. Do it on gray cars. That's a gray car. Car looks like that. So you project on it, gives it color. And this is the short version of my. I have more examples now than last time. And that's basically what we're doing, is doing magic. That's like a giant building that's been projection mapped. Cool stuff like that. Anyhow, I'm not talking about any of that, so someday maybe I'll give a talk on that. A guide to threaded coding. Stop sharing. This is, forget, in kindergarten, you learn to share. No, don't do that. If you have to share, okay, we'll use locks. And one I added recently, because people I forget that people forget. Don't call unknown code while holding a lock. That includes a virtual function or any callback, which is anytime you write a kind of a signal slot observer thing, you will have a list of observers and you'll lock that list and then you'll iterate over the list and then one of those guys will grab another lock and you'll deadlock. So don't do that. And then you should measure your code and measure your code again, because the first time you measured it was wrong. It's guaranteed when you try to measure your performance of anything. Then you change your algorithm, then you go back to 1. And most likely changing your algorithm involves share less data. You'll notice that algorithm loops forever, and you never get to lock-free. Lock-free is the last thing you want to do. If you do somehow decide that you can't get any more performance, or I should mention lock-free is also really good for, you don't get deadlocks. It's more robust. If a thread dies, that's okay. Even if someone does stupid things like killing a thread, which you should never do, a lock-free algorithm can deal with that. But if you do get down to the lock-free, don't forget to measure again, because there's no guarantee that the lock-free algorithm is any faster than just grabbing a lock. So basically, don't share and use locks. Almost. You take my joke away, actually. Rules of lock-free coding. What's the first rule of lock-free coding? Don't talk about lock-free coding. Now we're done. Gonna break that rule. I also have guide to coding while I have a room full of people who are stuck listening to me. So I'll take this opportunity. Macros are evil. Has nothing to do with my talk either, but I just thought I would put that in any chance I get. John Lakos is allowed to use macros. He's the exception. He gets mad if I say don't use them. In my slides, I'm not going to write out compare exchange weak or compare exchange strong, because that is way too many letters. I'm going to write CAS, because before we had standard compare exchange, that's the way I used to spell it. And also my slides are going to have code just crammed right in, and that's not usually my coding style, but it's got to fit on slides. So anyhow, we're going to talk about this MPMC queue, which means multi-producer, multi-consumer queue. So you have multiple threads putting data into the queue. John, you just missed a comment, man. I'm talking about you. It's good. It's okay, man. And we have multiple threads pulling items out of the queue. And what would probably be a much better idea is to have separate queues and have mostly single thread per queue instead of, and maybe a little bit of sharing when necessary. But this kind of queue where everything's going through one queue, what's that queue look like? That queue looks like a bottleneck. So you probably don't want to put everything through a single queue. But also, a queue with some sharing and whatnot is kind of a multi-threaded, multi-producer, multi-consumer queue. So maybe we make this queue and then we use it with other queues and kind of spread out the sharing and try not to share in all through one queue. Avoid the bottleneck. Anyhow, just burn this diagram in your head, because every slide's going to have a version of this diagram on it. I gave this talk a couple years ago here. And I did the first version of this, and we only got so far. So I'm just going to do like 5 slides of where we were, because I don't remember and you don't remember where we were. But basically, we have a queue that has a head and a tail. That's like every queue does. But how is this queue implemented? So you could implement a queue a million different ways. You could use a linked list inside of there or something like that, but who would ever do that? This queue is going to be a contiguous queue, right? So this is kind of theory queue. This is, real memory address queue. And it's going to have a buffer of things and a head and a tail, something like that. And it's going to be a circular queue, such that the head is now over there and the tail is on the other side. Okay. And our first compromise is it's not a queue of t's, it's a queue of integers, because that's a lot easier to deal with. And this will be like one of many compromises, which I like to call a comptimization, because it's a compromise for the sake of optimization, which is obviously a real word if you look it up in Google. You'll see the indistinct euthany houndity without comptimizing the histotic pata file of the existing tetminus. Tetminus, yeah. I just like to make fun of Google whenever I get a chance. Their first result was, did you mean comptimization? And there is one actual use of comptimization in low frequency radiation, something. So this worst part was, this is the same joke from 2 years ago, and you can still find, not exactly the same things are found, but you get the same answers as like second, third answer. So someone needs to work on their OCR. Anyhow, just to avoid people bringing it up, there's this idea of false sharing, where if I have head and tail and I want to eventually make those atomic and do atomic operations on them, an atomic operation on head might interfere with an operation on tail because they're side by side in memory. So what we probably do is put some space between them so they're not on the same cache line. And now just forget I said that. So just pretend that I did that. And if necessary, pretend that I did that inside the queue. And you can think about later whether it's necessary to do it in the queue and how could we avoid doing it in the queue. So the first weird thing about this queue I had, that we started last year, was that the head and tail don't point to the actual head and the actual tail. They tend to point somewhere behind the head and tail, and they're just kind of head-ish and tail-ish. They're nearby. And the idea is that you get the tail, and then you go looking for the head, knowing that it's near where you are. And you just find, you see some X's for when tail is trying to look ahead. It sees an X, oh, there's data there, oh, there's data there. Oh, here's the first one without data. That must be the real tail. And head does the same thing. It's sitting somewhere on non-data and has to find the real data. So of course, what do I mean by non-data? I've got X's in there. I have to have something in those blanks, right? Well, let's put zeros in those blanks. That's another comptimization. You can have any numbers in this queue except zeros. Everyone's okay with that? Zeros, I mean, who wants a zero? As you could imagine, if you wanted to start putting pointers in here someday, no pointers, special case. So that's another comptimization. And we have this other problem, though. Look at tail there. It's trying to find the first non-data. And if tail is so far behind that the queue has, there was some queue here, some other threads went along, tail didn't get updated, because for some reason tail is allowed to not update. The whole queue can fly by, and tail is now so far behind that it looks down and says, oh, there's the first non-zero. Whoops, that's the wrong non-zero, because tail's supposed to be on the other side. All right? What are we going to do about that? We need to tell the difference between that zero over there and this zero over here. Negative zero, that would be a good one. Yeah. How about we just use 1? So we'll just take another comptimization, and okay, 0 and 1. Who uses 1? That's not worthwhile. It doesn't do anything. You multiply by 1, that did nothing, right? Don't need a 1. And then, of course, we're fine now, right? Until the queue starts going around, and now we get 1s and 1s, and we have the same problem as having 0s and 0s. So yeah, let's start using 2s. All right. So on one hand, you could say, I'm going to, keep going up the thing. I'm going to take away half your numbers. That sounds like a lot, but look at it the other way. I'm just taking a single bit. What's one bit, right? You didn't need that bit. So yeah, how big is that optimization? That comptimization? It's a compromise, but well, at this point, optimization means works or not. So you know, any optimization goes from non-working to working is a good optimization. So there we have the black is real numbers and the red is not real numbers. So yeah, imagine that the red numbers are negative and the real numbers are positive. Or if you don't want to be a signist, you can have all negative numbers in your queue, and I will put all positive numbers in my encoding of the queue or something like that. Just take your pick. So yeah, it's only one bit. And last time, I'm sure we all remember, last time I showed this queue, I had this other comptimization where I put the kind of like this generation count inside the tail variable. So I kind of just stuff it in there, maybe make the tail variable a little extra big or whatever, just stuff that data in there. And oh yeah, right. So this is kind of where we left off last time. And last time I gave this talk, it was all about walking through the forest, because I used to do this. I used to work at BlackBerry, and behind the building was a forest that I would take walks, and all my work on lock-free programming is done in my head while walking. Because if you have a lock-free problem that has more than a couple of variables that you can't keep in your head, you're not going to get it right. So you might as well just do it in your head. I hardly ever put it on whiteboards or anything. It's just, you need to be able to think of all the states. You need to keep it all in your head anyhow. So, and it's also like, you know, you're dropping off the kids somewhere and you're like, okay, I've got 5 minutes. What are you doing, Dad? Oh, I'm working. Except for don't do lock-free at work. So I guess it's a hobby. It's kind of a weird hobby. So anyhow, I used to take these walks, and I did these walks through the woods so many times, and then one time I turned around and noticed that there's a poison ivy sign. It's like after, like at the end of my walk, I turned back and it's like, oh, poison ivy, which is kind of a good, you know, analogy to lock-free programming. So you just stay on the path and you avoid poison ivy. And then you know, that was the RIM buildings, actually, the BlackBerry buildings. Yeah, this is where we left the story last time, and so that's kind of the end of the review, and that's kind of where we left off. And now we're going to take a darker path through the forest, I guess. So that's kind of the end of the review. So we've got head looking for the real head. We've got tail looking for the real tail. Let's see what my notes actually say. And this one's, because it's wrapped around, you can, like, head is actually going to the far side, and tail has to go all the way around to find the real tail. Here's an unfortunate same problem. First data found is real head. It's like, nope, same sort of problem we had with tail. Thing is, last time I showed this queue, we never got to doing anything with head. It was all about tail. So it seems like we have somewhat the same problem. So we're going to have the same kind of, we need to tell the difference between the x's over there and the x's over here, right? So we need to find not just the first data, we need to find the first data of the correct generation. So now our queue is actually going to have a generation thing that we keep track of, and we're going to have to do this again. We're going to have 5s and 4s. And now I've compromised I'm not taking away half your numbers now. Like, I'm not just saying when there's no data, I have a number. I'm now saying when there is data, I have a number. So I'm not taking 1 bit anymore. I'm taking half your bits. So is this a kind of a big and not worthwhile optimization? Well, I'm going to say that usually I can take 2 ints. So now my buffer is full of 2 ints. And, you know, make this little entry structure that has data and it has a generation. And I'm just going to say you can lock free that, right? 64 bits probably. You can still do lock-free operations. If you've got a system where you need, you know, bigger system, well, maybe you have bigger lock-free things. You could maybe, a lot of systems you can do at least, maybe not 128, but you can do 96. So you could have 64 bits of data and 32 bits of count or something like that. It's like, if you have a tiny system where you've only got like 16-bit pointers or something like that, well, I bet you probably don't have big queues then either, right? So is this a optimization? Oh no, we still have this other optimization. We still have 0. I still need to know not only what generation of data is it, but is the data 0 or non-data, which I could just as easily hide inside the number or the data, but conceptually it's just easier for me to think generation is generation, data is there or not. So now we have tails looking for the first 0 data of the correct generation, and head is looking for the first non-zero data of the correct generation. So tail, instead of, if generation, we're kind of thinking we're on generation 4 here, so tail starts here and won't stop on this 0. It'll go around, increment itself. Like, you have to assume that when we wrap, we up the generation. And it gets over here and it'll find 0, 5, and it'll be the first 0, 5, and tail will be happy. And head will do something similar and find it'll skip past, it'll be looking for x4, it'll skip past x5. And then each should find the right place. So I should probably do all my slides in the weird cases where we're wrapping around and everything just to keep your brain working. But I tend to make my slides look like this, where it's all nice and contiguous and it's kind of a simpler case. So this is, tail is looking for that tail, which is just beyond it, and head is looking for the head, which is just beyond it. And this is a problem we ran into last time, where you're pulling data out of the queue, which is Pac-Man eating the wonk, 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 wonk. He's eating the things out of the queue, and you get to this point where you're going to eat the last item in the queue, right? And then after that, you're going to move head forward, and head and tail will be in the same spot. And then you start worrying about, shouldn't I keep head less than tail? And that was actually a huge problem last time I gave this talk, and there's all these ugly ways of making head less than tail. But now that I have, I've put this extra generation count inside the queue, head is now looking for exactly, not just a piece of data, and the last piece of data, but it's looking for x4. Head can come along, find x4, update, take that x out and leave a 0, 5, and now it gets to 0, 4, and head can actually see, whoa, wait a second, there is no data. It doesn't have to look at where tail is to figure out that the queue is empty. It can see by the queue that it's looking for data of x and 4, and there is none, because you already ran into a 0, 4, and you have to trust me that if you see a 0, 4, the rest are 0, 4s, and there's no x4. So now, the good part about this is that head can see what's going on without comparing itself to tail. And the queue is empty. And head and tail we don't worry about, because it's not a problem anymore. And we had this case, in the general case before I put the extra number in, we had this problem same problem when it got full. You can see where tail is, you can see where head is, right? There's one spot where the next item is going to go, that's what tail is pointing to, and head is pointing to the first entry. As soon as you put that one last place in, and now you look at a queue that just has x's in it, you once again no longer know where's the beginning, where's the end. So now that I've put this numbering system inside, I can see that it went from 5 down to 4. I know where the queue is full and where the start and end of the queue is. Right? So head is looking for x4. It can find it. Tail is Pinky. You all know, you have to know the names of the ghosts, right? It's important for the talk. Pinky is looking for a 0, 4 to find the tail. He can look around and he'll find nothing. Even if he looks through the whole thing, he realizes, wait, there's no room for 0, 4. So they can both independently tell that the queue is full. Oh yeah, tail will probably go off, come back around to 0, 5, still looking for a 0, 4 somewhere. Because tail is looking, if tail sees a 0, 4, it thinks that's, or an x4, it thinks that somewhere along the way there will still be 0, 4s. So it looks forward, and it looks forward, it wraps around, it updates itself to saying, I'm looking for 0, 5 now. And it will get back to a 4 and go, whoa, wait a second, I'm on a generation, I've gone around, I'm on a generation behind, so, yes?
So it seems that the encoding would take care of itself. Why do you need a head and a tail pointer?
You're so many slides ahead. The question is, why do you need a head and tail pointer? So let me go a couple slides and I will answer that even better. Queue is full. So this is, yeah, one slide, you're at least one slide ahead of me. So is this the comptimization? And my answer is no, this is an awesomization that we put the numbering in here. Because exactly what he's saying is all the information is in the queue. Head and tail can be anything. You can just look at the queue, walk through the queue, and find the right answer. Head and tail are just more, they're not comptimizations, they're just optimizations. It's like you probably want to start looking from where you left off. And also particularly the generation. Because you could actually do this starting at generation 0 at the beginning of the queue and just start looking and wrap the queue until you get to the right generation. But that seems kind of, you can also, we can get into a big discussion of like, how can I look at the front of the queue or the back of the queue and know what the generation is? Do I have to look at both the front and the back of the queue to know what the generation is? Like, oh, I see a 5, I see a 4. But when I see the 5 and I go look at the 4, it's no longer a 5. You can't see both ends at the same time. There's lots of things you can do. And I constantly play around with which ones I like the best. But that is the crux of this whole queue, is that everything you need to know is in the queue, not in the data structure that's maintaining it. So we should do some atomicization, because right now I have integers. So because the important information is in the queue itself has to be atomic, right? And not just atomic, it's going to be atomic with some sequentially consistent or acquire release or something. It's going to have some important memory ordering on those, because that's where the real information is. Like I said, I'm going to assume that that is small enough to make it atomic and still be lock-free. And then the head and tail-ish, I'm going to use a laxtomic, which is some word I made up. What is a laxtomic? It is, well, who's seen Herb's atomic weapons of mass destruction? It's actually just called atomic weapons, but yes. So he says you should never, ever use relaxed atomics. And I completely agree. So that lax atomic up there is a class where you derive from atomic and change all the functions to be relaxed. Yeah. Because why not, right? The purpose of this talk is to convince you not to do atomic operations. So is that okay? I am tempted to say, just argue right here, hand waving, that's okay, because like I said, head and tail are hints. They're not the real data. So using relaxed atomics and getting, this answer that has no dependencies on other information, it's like, there's no real information in head and tail. It's just like, look at the queue to get the real information. So I'm going to claim roughly that that's okay to make those all relaxed. And to kind of explain that a little further, in normal, if there's anything like normal lock-free, you have some data, it's got an X, you set it, it's got a Y, you set it, and then you set a flag saying, hey, this data is ready, right? And on the flag, you use a memory order. Probably you should just use sequential consistent, but maybe you use memory order release, because that's typically what you use when you're publishing some data. I wrote some data, I tell people that I wrote the data, so I publish it. On the other side, you look, hey, is there some data ready? You do an acquire, because you're going to acquire some data. And then you can read X and Y. And the whole thing is that the release on this side means, what's the meaning of release? And you can read like this huge thing in the standard. Release means before. So if I have 2 lines of code before the release, those 2 lines of code are before the release. Of course, you're probably thinking, isn't that always true, right? Isn't that how code works? It's like, no, code does not work like that at all. In normal code, that setting X could have drifted down below the setting of the ready, or, there's no real ordering on a single thread. And the standard and your processor both assume that there's only one thread in the world. It's kind of funny that the processor assumes that, since it knows that there's another processor sitting beside it and has multiple threads inside the processor. But nonetheless, they go, well, 99% of the time you want me to assume that there's only one thread, And most of this stuff isn't really ordered because from your one thread, you can't tell. And if it didn't do that, processors would be like literally 100 times slower. So it's a great thing that a processor goes, I'm just going to write these in whatever order I want. It's a great thing 99% of the time. And then this 1% of the time you say, wait a second, I really mean these must happen before that. You use a release. And on the other side, you say, I can't read this data X before I check that it's ready. There's also an if statement in there that has some logic, but think of like speculative execution and other strange things. You want to say, look, this has to happen after that, and you use an acquire. So if you put relaxed in there, this would all break. Because of that, the ready flag isn't a thing of its own. It's a thing that has relationship with other data. That's the important part. The ready flag will be completely consistent on its own. It'll always have the right value, but it won't guarantee the other values unless you use the right memory orders. So the question is, what other data does, not what data does head and tail rely on? What data relies on head and tail? And it turns out there's none, because all the data really relies on the queue. That's why I can make these relaxed. They're just hints. So we make those two are these relaxed atomics. And I'm going to stop calling them head-ish and tail-ish, which I now think that was a mistake. All my slides should say head-ish and tail-ish, because otherwise you forget. And I'm a big guy on proper naming. The proper naming for these variables, it's head-ish and tail-ish. To remind you every time you see them that they're not really head and tail. But I wasn't going to go through 100, 200 slides and fix that. Someday I will. So then the next question is, I have this generation count. Should it be atomic, relaxed atomic? What is it? And I'm going to say same thing. The generation count that's inside the queue, that's in every entry, that's got to be a strong atomic in the entry. But the generation of what generation are head and tail in, that can be relaxed. It's the same thing, it's a hint. Now, we might have a situation where head and tail are communicating through generation. Maybe there's a dependency between those three variables. So that's something we have to watch out for. But right now I'm going to say they can be relaxed. So that's our class. So what does push look like? And it's often in these talks I go like one line at a time and I build up the function. Now, here's the function. But it's a very small function, so why not? You load up your variables into temporaries. You got a temporary generation count and temporary tail. And then all you're doing is walking, like I said, you're just going to walk through the queue with the is 0 to find a 0. And it's not just is it 0, but is it 0 of the correct generation, right? And because that's a relaxed atomic, on most platforms, that is free. That's just like not even doing an atomic. You're searching for it through a queue for an integer. It's like, whoa, that's pretty fast, right? It's very close to the same, right? And then if we don't find it, we increment, like in the first while loop there. And our increment just has to make sure if it goes off the end, it comes back to the beginning, updates the generation. And then if we do finally get there, let's see, I actually had slides for this. Blah, 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 like I was just saying. We walk through, we increment. That one's not 0 yet, so we increment again. This one is 0, and you're like, great, we come down here. And now, even though we just saw that this was a 0, on this next line of code, what is the number in there? Well, we have no idea, because it's multiple threads. So someone else could have changed this value. So when we get to this point, we have to do another atomic operation. We have to reread that value and say, hey, this was 0 just a second ago, a 0.4. Is it still a 0.4? And now we're going to do it with a cas, because it's like, if it's still a 0.4, then I want to put x there, right? So we do a cas, and we've entry is our new, what we want to put in there. Whatever value came into the function, we're pretending it's I guess we don't know what it is, some value. Generation is going to be 4, and this is not relaxed. So we put our P in there for Pinky, and we're all happy, right? Or, whoa, Michael warned me about this. Pinky. Or we came here, we went to put a value there, and we found a C in there for Clyde. Told you had to know your characters. And if that happens, the while loop will the CAS will fail. That's why it's in red. We jump back up to the loop, and then we just go over again. We just like, okay, go back to finding a 0. And this is the fundamental nature of lock-free programming, and the term lock-free is that you only fail when someone else came around and did something that succeeded. In this case, Clyde. A CAS loop, which is what I tend to call these things, a CAS loop will re-loop on progress, right? Someone made progress, so you fail and you loop around again. A spin lock loops on progress if another thread is making progress. It also loops if that other thread's doing nothing, because it's just waiting for a flag to tell me that other thread was done. If that other thread got shut off by the scheduler or something, a spin lock will still just wait. No one's making progress. A CAS loop will only loop back if someone else did something. That's lock-free, right? If you look at Herlihy's definition, it'll say a thread made progress, guaranteed. Either you made progress or someone else made progress. Someone got in your way because they were making progress, not because they just stole a variable and told you to wait. So we will again see that there's a value there now. We will increment, look at the value, we got a 0, and then we have to do this one more time, and then maybe this time we succeed, and now we're happy. Are we happy? When do we increase the generation in the variable that's like not in the queue, not inside the queue, but the generation variable in the. Also, when do we increment tail? Because I mean, so far I've been incrementing temp. So exactly. It will increment the temporary generation of the thing walking around, but the real thing that tracks the generation at the end of the day isn't being incremented yet. So that's one question, is we have an incremented tail or generation. Turns out this would still work because we'd always start at 0 and we would go through 5 times to, or whatever we had to do, or 100 times. The best part about that, yeah. Now the scary part about that is if you wrote tests for this and you forgot to those tests would probably all pass, and those tests would probably be small enough that you would never notice that every time you add more to the queue, it just gets a little slower. Every generation, the queue's a little slower, and you're like, I don't know what's going on, just a little bit slower. So here's the thing, there's that question of we didn't update some stuff, but there's also this other question, is like, what about this case, right? We just did one case. It was a simple case of being, inside the x's when we started. Here's a case where we're inside the zeros already, but it's a 0.5. We're looking for a 0.4. Wow, I'm jumping back and forth, sorry. Maybe I don't even know what I was trying to say there, because I think I said that. Okay, I'm just going to go on. I will get back to that. I know there's more slides for that. That question, should we update generation tail? So let's say yes. Let's just say we magically update those variables for now. And now I wanted to mention, what about this case? What about when it's wrapped around and we got to get to the other end? And I'm going to go fast because I was told I'm already a half hour in. It's going to correctly see the is 0 as fail. It'll correctly, hopefully, do the wraparound in the increment. It comes around. It lands in the right spot. Yay, it still works. Here's another example. What about for right on the edge? It's always a good question to check that there's no X before the first entry, but it's way on the other end. And I'm going to claim, yes, it will find the right spot as well, because temp starts at 0 again. it gets to the right spot. But then what about this case? You've got nothing in the queue. There's no X's. And I'm going to claim that, whoa, what happened here? Oh, the empty case works right away. It's just like, bam, you can find that really quickly. How about this case where tail is past the real tail, right? The real spot we're looking for is that first 04, but we're already past 04. And now we come into the code and go, let's look for a 04. What happens? I think you already saw me put an X on the screen. It doesn't work. Anyone? It appears not to work because we come into this while loop and we'll search for 0, we'll find that 04, and it's the wrong 04. The question is, how did we get to this state where tail is ahead of the real tail? This is when the one guy, Sebastian, 1 second in, he's like, that can't happen. Just instantaneously, he's like, that's wrong, it can't happen. Can't have tail past the real tail. And I'm going to claim that is an invariant. Tail with the right generation will never be ahead of the real tail with the right generation. You can obviously have them pointing past each other, but not with the right generation. So, my claim why this works is because the temp always increments past, the tail variable is here, temp goes forward, and then you set the real tail based on temp. So real tail is always lagging behind. There's no decrements in the code anywhere. It's kind of part of it. You have to think about multiple threads, what each thread's doing, but you kind of get this feeling of it's always going forward, and they go forward even when they wrap around, they still go forward. Man, I got to remember why I highlight things. That's where it gets written into. Just skip that. That's where generation gets written. So it's also ahead of tail being written because update isn't being called yet. Then update happens before the rest.
Update tail and generation at the same time, like in one atomic action, or?
No, because once again, tail and generation are just hints. So I'm going to. That's a good question, actually. I'm going to solve that later, anyhow. So I feel I have to go quickly here. How far behind can tail actually be? Like, can tail be at 0.3 and we don't have any 3s at all? I'm going to claim yes, it can happen. It happens if that whole do while loop happens a lot by a lot of threads. So the queue gets full of things and no thread gets to update. So the queue can get really full and tail is miles behind. It can be like 10 generations behind, probably not, but it could, and that will be a case where it's going to be like over looping, which you could optimize by looking at how far behind you are. But so, is there an invariant that generation is at least 4? There isn't, and there doesn't have to be. It doesn't matter. So I'm going to claim this case is fine because it never happens that tail is on the wrong side. This is another edge case that, tail's on the wrong side, it's all empty, and I'm going to say, that's actually the same thing where that can't happen because of the invariant, so we're good. This case, and I think I know what I changed. Just going over the edge cases again. Right. This is the last edge case. Of course, I leave that last edge case the good edge case for last. The queue is full. Tail is looking for 0.4. We're at X5. We'll go along looking, I thought I had more slides for that. We go along looking for X04 and we don't find it. So we'll go loop around. Now we'll start looking for 0, 5. We won't find it. Then we'll look for 0, 6. And we'll look for 0, 7. And we'll just go on forever looking for that value. Eventually, we'll wrap the integer, overflow the integer, and then we'll start, maybe at some event, this is another one where this code could just keep running because sometime there will be a 0 in the buffer, and at some time you will wrap your integer enough that you'll find that 0. Probably not what you want. So I'm going to stick a little bit of code in there that says if the entry that I'm looking at is a lower generation than I'm looking for, then I know that I'm done. Like, so I will start looking for 0, 4, and I'll start looking for 0, 5, and I get to here back to 4 again. And I go, whoa, I'm going backwards in time now, so I must be done. And I know that the queue is full. So I return queue's full, or I depends how you want to do it, but let's just say I return queue's full. You could try to do a wait until it's not full and things like that. And the best part about that is you return the queue is full. You don't return the queue is full. You return the queue was full. And that might not even have been true either, but it's like it looked full to you and it was full for like just a split moment. It's from the outside, you can't tell the difference of whether it was ever really full or not. I can tell you it was full and you will believe me. That's often the case, right? It may not, yeah, but it looked full to me, so I'm going to return that it was full, and you can't tell that I'm lying. So it's, yeah. I mean, even if it was truly full, as soon as I start to do the return, it might not be full anymore. So what's the difference, right? It happens all the time in log-free programming. It's like, so I changed the code now. So in theory, I have to recheck all those cases, all those edge cases, right? Because you made a change of code. This is me rechecking all those edge cases. And then we get to this point of, if you recall this slide, of updating generation and tail. It's actually going to look like this. I have to pass the old tail and the old generation in. And then update is going to look like this. It's going to, because we were right there and we wrote the P, once we get into update, we have to increment one more time because we want to put the new tail there. And we're going to cas because at some point, old tail was there, tail started there, we've moved temp along, and now we want to know, has tail changed since we last saw it so that we can update it? Or did someone else already update it for us? Because at this point, the queue looks like this, right? The whole queue might have changed. Tail could be somewhere else now. It could look like this now. We don't know what it looks like. Whoop. Ah. That's a great way to do it. We all know what slide number I was on, right? Ooh, over here. Okay, we're here. We're trying to update. We don't know what the queue looks like. Could it look like this, where the real tail is right there? So if it looks like this, and the real tail is right there, and we go to update tail to over there, then we've broken that invariant I just talked about. We'll have tail past the dotted line where the real tail should be. So we really don't want to do that, right? We'll break our invariant. I'm going to say that can't happen because we had 4s there, and now I'm saying, oh, what happens if it looks like this now with those 0 4s? Once you've got 4s with data, you'll never get 0 4s again in those spots. They will at least be 5s or something bigger. So I'll never get this case where I put that that I'll never get the case where tail is behind where I last thought it was. So you will never see it looking with these 5s and 4s like that. However, you'll see this, 6 and 5s, because it's gone around. So now I look at tail in the CAS loop there. I look at old tail, and I say, yep, it's pointing at the exact same location it used to point at. So I will now update it to the other location where temp is. That's what the CAS loop the CAS instruction will do. And I have now broken my invariant just like a whole loop later. And you probably will rarely find that because it's another case that you'd have to do a lot of testing before you ran into it. This is an ABA problem. Let me explain that. So here is A. We've got old tail and tail, and we're looking at the value of tail compared to the value of old tail. And we go, okay, they're both at entry 7 or 8 or whatever number it's at, right? They're right there pointing at that cell. And then we go along and we do some work, and that's B. There's some state of the machine, and we don't know what it is. And then we decide, okay, we're here now. We want to update tail to temp. And tail, you go, tail hasn't moved. It's at the exact same spot old tail was. So I can do that update. Problem is that the old A and the new A aren't the same color. One is purple, one is blue, obviously. So we need to take the purple and blue and encode it into tail and old tail because we've lost that bit of information. Things look the same, but they're not really the same. So we just stuff it in there. You can either imagine stuffing it in there, like put the number beside, like cram 2 integers together, or you can also just think of tail and old tail don't have, like they just always increment forever. And eventually you need to worry about wrapping around, but we're not going to worry about that right now, which are essentially equivalent things. Either old tail never gets past 16 or whatever the size of your queue is, and it just goes back to 0, or it just goes on forever. And if it goes on forever, then you'll have to do the mod whenever you access the buffer, right? So equivalent ways of thinking about it. So now when we try to see if tail has changed and check like, has the world changed on us, we can see whether it has changed or not. In this case, it is the same. And in this case, we'll look at tail and old tail, and we actually see that they're different because we've added that extra bit of data to them. So the cast will fail, and we won't update tail, and we won't have broken our invariants. And then generation has a similar thing. It's like, what generation are we on now? I don't know. We were on generation 4 a second ago, but the whole world changes between every line of code. And I'm going to say that generation count, the temporary generation count, just has this tendency to always increment. So what we can do is say, as long as the generation we want to set it to, as long as it's greater than whatever generation it currently is, update it. Even if it's changed, someone, Inky might have come here and changed generation from 2 to 3, but I think it should be 5. I don't look, oh, if it's 2, make it 5. I look, if it's anything less than 5, make it 5. Because why not? Let's get up to the most recent. And I'm going to claim this all keeps our invariance in check. And that is all that code for push. Now I have to figure out how much to do in the next 15 minutes. There's some interesting things about that even. Oh, the one question is how many relaxed versus non-relaxed operations are there? Ends up being like 3 or 4 relaxed operations and 1 non-relaxed, which is pretty good. There is a problem, of course, that there's really no such thing as relaxed CAS on like x86 or anything, because it has to do, it's an if statement. It's not just, oh, I'm just setting this variable or something. It's going to be as slow as a non-relaxed CAS. So that's not as optimal as you would like. So the next question is that same thing. Do I even have to, for some of that, like the generation, should I even check if the generation's changed, or should I just set it? Just like, I might be behind, but the chances of me, it doesn't matter if I set it behind. I'm probably ahead, so just set it. Don't even check if you're ahead or not. Just assume you're the last guy. There's a lot of little optimizations you can do because we assume that these are just hints. Okay, at least we can get to pop. Same sort of thing, head is looking for the first non-zero data instead of the first zero data of the correct generation. And if the push code looks like this, the pop code looks like that. And hopefully that looks very similar. And I basically put in red every line that's different, right? You're looking for data instead of zeros. Instead of checking for this less than thing, we're going to check for equals 0, and we can find out that it's empty, or equal, if the generations are equal, we know it's empty. And we're going to be updating head and returning some data. And we have a, very important, we have an acquire operation instead of a release operation. And I have this one problem that I keep talking about this generation thing, and I have head needs a generation and tail needs a generation. And in this example, those are different generations. So now I've got 2 generation counts. And once you've got that, it's like, why don't I just put head and head generation into a struct and tail generation into a struct? So I made this struct called gen I for something that would fit on slides. It's generation plus integer. And it is now the same struct as the entry itself. They're all 3 generation, an integer plus a generation count. And you know, you can assume that operator less than equals default is a C++ feature. It's not. So this turns out to be all the code. And it all fits on one slide, surprisingly. So that's why this is a simple lock-free queue. And all you need to do is look at all these different states and check that every single line of code is valid for any one state. And when you go to a second line of code, check every state to see if it's valid. And of course, the first question is this all the states? Or are there more states that I'm not putting up here? Or are there actually less states? This state, right, how is this any different than these two? Because the algorithm only sees one entry at a time. So that state in green is really a combination of those other 2 states in yellow. The algorithm can't see the whole queue, it sees one entry in the queue. So in a sense, there's actually not this many states. And what you really want to do is look at the entry you're looking at, because this is, every diagram I have looks like this. Every diagram should really look like that. That's all you can see when your code, right? I can only see what's here now. The whole thing is that you build up a few assumptions or some invariants so that it's like, if I see this, I know something else, but all I can see is one thing at a time. So for that X4, it can be any one of those kind of configurations, except for maybe 5s or whatever, same idea. And you know, when you're, you know, the next, from this step to the next step, you could be in a different state. In the next step, you could be in a different state. And every step of the way, you have to check what state you're in. And you can do it this way and just look at those values and say, well, if I'm looking for a 0,4, if I find a 0,4, stop. If I find an X4, there's a little fork in the road. And if I find a 5 or an X5, I just keep going. So that narrows down all the states that we have to deal with. And I have to remember what this case is about. Yeah, this is that when you find out that the queue is full, you would actually, I don't update head and tail there. I don't update tail when I should. I can search through the whole thing and find out it's full, and I just leave instead of like at least telling people what the last thing I saw was, but small problem. So this is what lock-free programming looks like, right? Have all the code in your head, have all the states in your head, and do the code. I'm really close to being out of time, so that's the part about updating tail. This is like the real half of the talk that I can never get to next time. I claim these are some of the invariants that we're trying to maintain in this queue. That tail is always less than real tail, head is always less than the real head, that it actually is circularly contiguous, like that I didn't end up putting a hole in there somewhere, because then everything would break. that the entry generation is always like 5, 4. There's only ever 2 generations in there. It's always higher than lower. Tail only increases and it adds data. And then head only increases when there is data. So that should be able to, for me to prove that head is less than tail. But I don't really care if head is less than tail because it no longer becomes a problem. And ordering guarantees. Something that is hiding in here is, what guarantees do you have on, I have a thread that put in 1, 2, 3 into this queue in order. What order do they get pulled out of? They might get pulled out in any order in a normal. You have to assume that if I have a multi-threaded in and multi-threaded out, you didn't care what order I put those in because they're coming out in whatever order and they're getting processed in whatever order. On the other hand, maybe I write this queue that is multi-threaded, multi-producer, multi-consumer, but you happen to use it in a single-threaded case. Then you're like, hey, I know I put 1, 2, 3 in an order. Why didn't they come out in order? Like that would be, if you only have one thread or whatever, you could see this now. So my queue actually tries to guarantee that. For a single thread that put in A1, A2, A3, you could see that that thread comes out in order. Even if you had multiple thread ins and one thread out, you would see A1, some other stuff, A2, some other stuff, A3. That comes down to also what are the semantics. I didn't explain what the semantics I'm going for, and that kind of ties in what invariants are you trying to maintain. And in theory, I would try to prove something like range is circularly contiguous, which in 10 seconds I will do. Which means, did I write it in the right spot? So 0, we start 0, we walk through this, and I will write it in the right spot. Oh, awesome, 0 case works. It's always good to know that the first case works. Then we assume that we've gotten so far, because this is proof by induction. It's like, okay, now we have some things in the queue, and then we just have to prove that the rest of it works. This relies on some of these other things that I've yet to prove, right? So this proof can go on for about an hour of how do you prove lock-free code? And it's very much one step at a time. And things like, how do I know that real tail, like we've kind of talked about, but it's like, you have to look at, well, it gets set by, temp gets set there, it came from here and it came from up there. You have to trace backwards, where did this data come from? Is it always increasing? Does it ever decrease? And when I was walking through all this, I ran into this case of, like I said before, it's like tail will never get set until after everything else, because it's the update happens last, right? But this code is actually relying on, am I quite at the right spot? Yes. Could this ever happen? Can line 1 happen before line 2? And you're like, that can't happen, because like line 2 is basically an if statement, and how do you go into the if statement? Like, it's if this, you'll fall out. So how do you go into an if statement and do something before the if statement, right? But at the same time, I'm like, well, I don't have an acquire. I don't have a before, I don't have an after means after here. I've only got a release. Everything before happens before, but I don't, other than the logic of an if statement, which you have to start to think about when you're doing lock-free programming. I don't have anything that says, well, it's, we also don't do speculative writes, so the chances of something being written going upwards. But you do have this, I have this ordering between these two variables, and the code is, this is where some information passes between threads. Some other thread is might be setting the buffer with this release, and I have an ordering relationship where tail is saying, well, I know the buffer is set, so I will know that I will never see 0.4 and problems like that. So at least technically, I feel there's a relationship between these lines of code, right? Like I'm worried that all those X's will happen later than the setting the tail, and it'll get out of order. At least there's a logical relationship, even if it doesn't happen in a current processor, or there's no compilers that optimize it or whatever. But technically, I think I need an acquire release there. And we could spend a whole bunch of time to decide, do you need to acquire release there? Or do you just go, I'm going to put a acquire release there because it's safer? So leave that as a question for the... we could, go read the standard word for word and try to decide how that works. This is what makes me worry about it. That simple line of code there, read the value at some address. That's two separate loads, right? You have to load what's the value of the pointer, then what is the value at the pointer. Can those two lines at the bottom be reordered by the CPU? And of course you're like, how could it be reordered by the CPU? The second line has to know what the first line gave as a result. Of course, on an alpha processor, those two lines can be reordered in the memory. And I could spend some time, if I had more time, I'm trying to explain how in the world can something like that happen. But you have to imagine that one way of imagining it is it's already read pointer before, and it's just going to use that same, it's like, oh, I've already got that in the cache, or I've already got that in, I just read it 2 seconds ago. Why would I reread it when I'm the only thread around? So it can in effect reorder those instructions. And that's my question would be, does anyone here understand memory order consume? And I guarantee no, because the committee doesn't understand memory order consume, and we've put a comment in the standard saying, don't use this right now, we're still figuring it out. So that's what this is all about. So that's what makes me wonder about, I don't think those lines can be changed, but then I'm starting to I start questioning myself. And that is, I managed to get to the end. Looking back, we did push. Awesome. And pop. That's how far can you get? That's a lot for a lock-free. And we started talking about invariants. I'd like to talk more about the invariants later. And I'd like to point out this thing. Someone did this project called the Ptolemy project, where they wrote a kernel and an OS and all stuff at Berkeley. And they said, let's make this the best practices possible. We will do design reviews, code reviews, nightly builds, regression tests, code coverage, 100% code coverage, reviews of the concurrency. They brought in concurrency experts to review this code in the kernel, and it ran for 4 years and then it deadlocked. Right? So the whole idea of do I test lock-free code? Yes, you need to test it. Do I guarantee that those tests tell me that it's right? No, I don't guarantee those tests at all. So then you don't really do them. Well, it guarantees that it won't, you won't have a problem as often as if you didn't run the tests. It really comes, because for a lot of industry, you look at this and you say, bug once every 4 years, I can live with that. Maybe that's, if it's like a medical device, maybe you have to make a different choice. But if it's my phone, my phone's not going to run for 4 years straight, so who cares? But it does. This is also here to scare you. That's the point of this slide. And looking ahead, I have a queue that looks like that. When it gets really full, my goal is to put a marker in there and allocate another queue that's twice the size. This is why the goal of this queue is to be a growing and shrinking, mostly contiguous, multi-producer, multi-consumer lock-free queue. I think that's a lock-free queue that grows forever is a queue of any kind that grows forever is a bad idea. It means you have a problem in your system. But it's the most complicated queue I could think of, so I thought I'd write it. And the plan is to have this other side buffer here that only has to be 32 numbers to track. Is anybody using, are those new queues that you've constructed, are they still in use, or have they become empty? So the idea would be, of course, this is still circular. You go here, then you go up there, and then you go up there, then you come back to here, and then you loop around. And then at some point, if one of those gets empty, you remove it again. But someone might be in there looking around for something. And so you have to have reference counts and all these other things. So this is why this is called part 2 of N. This queue, this is my next 5 years of talks. And I want to get not just ints, but structures. That's someday we will have structures in this queue. And then we're getting out of the woods. We're at the end of the thing. That is the code. I think I am done. I went fast because, sorry, and if there's questions, we don't have much time, but I will stay around and talk about this stuff as long as you want. But I'm going to say that is my last slide. Thank you.